Right, so what I've set up is a table called transformed height data, and in my first column I've just literally got square root of height. So what I'm going to do is, I've already done this on another piece of paper, I'll just go through. So you're just going to square root the first height, so it's just going to be square root of 0.12, and then square root of 0.1, 0.08, 0.06, and so on and so forth. So I'll write the first answer, and then so the square root of height, we'll just round it up as well, so 0.3, we'll go 5 because it's 34641. So we'll go 0.35, and I'll do the rest later. Now, so the max and the min. So over here, we have our uncertainty is 0.005, so half a centimetre. So what we want for our maximum value is the maximum this number could ever be. So the maximum this could be is just 0.35 plus half a centimetre, which should give me, what should it give me? So this is the original maximum as well. So it's 0.12, I should say, plus. So it should be 0.12, and then we're going to add that 0.5, which means I just get 0.125. Conversely, the minimum the height could have ever been would be 0.12 minus the uncertainty of half a centimetre, so that should give me 0.115. Is that correct? Yes. Yes, it is. 115. And so on and so forth. So I'll just do the next one just so you to get the idea of it. My next height was 10 centimetres, so 0.1 metres. The maximum this number could have been would be 0.105, and the minimum that number could have been would be 0.095. So we'll just write those in. So we're going to have 0.105 and 0.095. So notice that these square root heights, the reason I'm doing the maximum and the minimum is you'll see in a second. So I'm just going to pause the video, fill out, or do the calculations, fill out the columns, and then we'll go over to the new uncertainty. Now, for your new uncertainty for the height, what you're going to do is you're going to forget about this square root of height. You're not going to just square root the old uncertainty, because that would give you goodness only knows what. You are going to square root the largest number height could have been. So that's why we have the max here. So you're going to square root the largest number height could have been, which is your max. You're going to subtract that from the smallest number height could have been, which is your minimum. And that this here, the square root of the max minus the square root of the min, will give you your new range. So as we have over here, do we have over here? Yes, we do. In our time, when we did before, we had the range and the time, and then we halved that to get the uncertainty. So that's why I've got the 0.2. And I have two columns here because uncertainties should only ever be one significant figure. So notice I just did this without thinking over here. 0.005, that's one significant figure. So when I get my new uncertainty, I'm going to put the unrounded, and I'm going to put the rounded. So the rounded has to be to 0.1. So we'll do the first one. So we're going to have 0.125, so we'll square root of that, minus the square root of this, divided by 2, and that should give me, what should that give me? 0.0072. Right, and so rounding this up, that's just going to be 0.007. So I'm going to pause the video and do the rest, and then we'll have a discussion. Right, so I've gone through and processed all my data. So now I have, these are the new uncertainties for the transformed height data. So now when I draw my new linear graph over the page, I'm going to add my error bars. You don't need to really add error bars to your non-linear graph. In the mark schedule, it only really asks for one set of error bars, so don't worry about it. Just do everything on your linear graph, and then you can derive your equation from there. So this here is going to be, these are the uncertainties I'm going to be using for my new error bars. So I'm going to pause the video and set up my new linear graph. Right, as you can see, I've set up my linear graph for the square root of height versus time for emptying a bottle of water. You'll notice I still have time along the y-axis just as before because I haven't altered the time whatsoever, so that's just the same. But what I do have is I have the square root of height, and notice I've square rooted the units as well. A common mistake I've found for my students to make is they'll put square root height and then they'll put meters just over to the side with no square root above, and if the line up here doesn't go over top of it, it can be a little bit ambiguous. So either make sure your square root goes all the way across, or just have a separate unit with the square rooted over top of it, or squared, or 1 over, depending on what the relationship was. I have all the values along the x-axis times by 10 to the negative 1, so that would just shift everything across 1 decimal place. You do have to be careful though, because as you go up the scale, things can change a bit. So I had one student caught out with doing this here. Try and do this here, you're less likely to get caught out with mistakes, but this one here, if you times 10 with a negative 1, it just shifts everything across 1 decimal place, so it's not that big of a deal. So what I'm going to do is I'm going to pause the video, and first I'll plot the first one, and then I'll pause the video and just do the rest. So for the first height, we have 0.35 meters. So the first height goes with the first average time over here of 0.5992. So what I'm going to do is I'm going to go across to 3.5, which is here, and then up to 59.92, so it's basically 60. So I'm going to go up to 60. Oh, I should have left myself a little bit of space, but here's the line here, but it's not going to matter. Oh, it is probably going to matter. There we go. Okay, I'll pause the video, add in all the rest of the dot. Right, now I have plotted all my points. You'll see it pretty much is a straight linear line. So what I'm going to do is get my ruler and just do a line of best fit that goes through most of them. There we go, that goes through pretty much all of them. And I'm going to extend it through the x-axis down below, for you'll see why soon. So I should have given myself a bit of extra space, but just whatever. I'm going to pause the video and continue this down, and then we'll have a look at the y-intercept. So here we can see I plotted my graph down, and I have a y-intercept of negative 26. We'll put the units in there seconds just because it is. And we'll have a look at that later. So now what we're going to do is we are going to we're going to plot our error bars. So I'll plot the first error bar. We'll start off with, what should we start? We'll start off with time. In fact, we'll have a look at the error bars. I'll pause the video and then I'll continue. Right, so what I've done is I've added in my height error bars, but I had a look at my time uncertainty to do the time error bars, and notice that each uncertainty is pretty much about half a second. If you look on the graph, half a second is just too small to draw, so I couldn't do any vertical uncertainties, otherwise you wouldn't be able to see them. And so I had a look at my horizontal error bars, and we have 0.2, 0.1, 0.1, pretty much 0.1, pretty much 0.1, slightly less than 0.1, but close enough. So on my graph, I figured out how much 0.1 was, and I think 0.1 is about 2 millimeters. So if we go to here, we have 0.01 meters, so it's about 1 centimeter. Each one of these represents, so this here is 35 centimeters, that is 15 centimeters, 5 centimeters, 2.5 centimeters. So 0.1 of a centimeter is roughly about halfway between here and here. So my first error bar, although this should be a little further about, is about from here to the center, which is roughly about that, and then this should really be over a bit, but I won't worry about it. And then all my next error bars were 0.1. So this was 0.2, as we can see. I got it here. 0.2 for the area and the transformed height, and all the rest were pretty much 0.1. So I've gone 0.2 positive, 0.2 negative, 0.1 positive, 0.2 negative, 0.1 negative, so on and so forth, all the way up. Now I'm going to add my uncertainty in the gradient. So what I do is there's a few ways to do this. You can do 2 uncertainty lines, or you can just do one and find the difference between that and the actual line of best fit. So I'll just do the one between the, we'll draw one uncertainty line. So we go from the lowest it could have possibly been to either the highest or one of the other highest. So you're basically just trying to find a line that best fits, that's the steepest gradient it could possibly be, but still get inside most of your error bars. So if we have a look, we'll extend that out. This steepest gradient line just fits inside that one, not quite in that one, and that one, and that one, and that one, and not quite in that one. So it's a bit of a, I'm not really sure whether there's a certain rule to it. I've never come across a rule for it. The computer does it, goodness only knows how. So now what I'm going to do is I'll pause the video and I'll find the gradient for both of these lines, and the difference between this line and this line will be my uncertainty and the gradient, and then we'll derive a formula. Alright, so what I did is I first found my gradient of my actual line, so of the best fit line. So I just did the triangle method where I drew up, drew across, so I went, this is my x2 value, x1 value, y1 value, and this is the, and then I used, if I go up that line to here, this is my x2 value, and that's my y2 value, so I went, we can see 47.5 down here, minus 17.5, which was roughly there. And then I made a, this is where you can get caught out. I went 3 minus 1.75, and then quickly realized that this is times 10 to the negative 1. So I had to go 3 times 10 to the negative 1, and then minus 1.75 times 10 to the negative 1, which is this one here. And that gave me my gradient in my graph, which is 240. Which seems about right. You're not going up very much on the x-axis, but you're going up a whole lot on the y-axis. I got 24 to start with, and I thought that's a bit strange. It should be a lot steeper than that. And then my error line, so my steepest gradient, which is this line here. This is my x. Here's my x1. Here's my y1, and I did the same way up to up here. Down here is my x2. That's my y2. So I just went 62.5 minus 6 over 0.35 minus 0.15 instead of going times 10 to the negative 1. And that gave me the steepest gradient of 282.5. So the uncertainty is just the difference between that and that. If you do a steepest gradient and a shallowest gradient, that'll give you the range, then you just go half the range. So if I did a shallowest gradient line, that'd probably give me a gradient of about 200. And it would still give me roughly the same amount, but there's multiple ways to skin a cat, so you can do it however you like. So the difference, here's my gradient, here's my uncertainty in the gradient, which was 42, because it's just the difference between that number and that number. Noticing that all your uncertainties have to be in 2 significant figures. So now we can write the final formula. Time is equal to the gradient, 240, plus or minus 40 times the square root of h height, and then minus, where was our y-intercept, 26. So this is our final formula. Now, what to get achieved, really need to compare this to the formula that you were given. So if you write them side by side, t is equal to, I'm just writing off the other piece of paper, in fact I'll scribble that out, we'll use the derived version. Where is it? Here we go. Here's a derived version, d squared over d squared c, all the rest of the rubbish. So let's do that now. Let's go d squared over little d c, square root 2 over g, bracket, square root hi minus square root hf. This here is really hi, so I'm going to put hi just so it makes it a bit clearer. And now what we're going to do is we are going to make a comparison. So over the page, I'll peel this over, we're going to compare the theoretical gradient. So we're going to write theoretical gradient, which is simply just, what do we have? We had d is equal to 0.9, little d is 0.005. If we plug, and the flow coefficient is 0.61, which was given, if we plug that into this formula here, that should give us this. So here I've plugged in my d equals 0.09 and little d 0.05, and it comes out as 239.94. Comparing to the actual gradient, actual, can I spell that correctly? Gradient of, what was our actual gradient? Here is our graph. Here we go. 240. So that is crazy spot on. In fact, that is astounding how accurate that actually is. But we have a big problem, is this here. If we go back to the actual formula over here, our y-intercept should be this gradient times, in fact this should be meters, shouldn't it? Pause. Right, if we're comparing to the actual intercept, that should be, where we got over here, HF of 0.01. If you square that, you just get 0.01 out again. So if we go 0.1 times 240, that gives us 24. So theoretical gradient, and I'll put theoretical intercept CYPT is 239.94 times square root of 0.01 equals 24, basically. So our gradients are pretty much smack on. So we got 240 and 26. We are well and truly within our uncertainty. So what we'll do is we'll pause the table, or pause the video, and have a look at extreme values. So I've just said, comparing to the actual gradient of 240 and the intercept of 26, we can see that our experiment is very close to the predictive model, because the theoretical gradient is 239.94 and the theoretical intercept is 24. So smack on for the gradient, and smack on, or almost smack on, for the intercept, and we don't even really need to worry about our uncertainties. Right.